Assalamualaikum warahmatullahi wabarakatuh. So today we will go talk about misconception about changing concentration of substance during the reaction. Before that, let's we know about reaction rate and the factor of reaction rate. The rate of reaction is a measure of how fast or slow a chemical reaction happens. It refers to change in the amount of a reactant or product over a certain period of time. To calculate the reaction rate, you can use a simple formula. The rate of reaction is the change in the amount of reactant or product delta divided by the time it takes for that change delta time.
Okay, now it's time for us to know the factor of reaction rate. The first factor is concentration of reactant. The reaction rate increases when the concentration of reactant is higher. This is because a greater number of particles in a given volume leads to more frequent collisions, which increases the likelihood of effective collisions. And the second factor is temperature. Temperature peak affect how fast a reaction happens by giving particles more energy. When the temperature increases, particles move faster, which causes them to collide more often. More particles have enough energy to start the reaction, leading to more successful collisions. For example, sugar dissolves and caramelizes faster in hot water compared to cold water. And the next factor is catalyst. Catalysts speed up chemical reaction by lowering the activation energy required for the reaction to process. They provide an alternative pathway for the reaction without being consumed. And the last factor is surface area. The reaction rate increases as the surface area of a solid reactant increases. A larger surface area allows more particles to be exposed and available for collisions. Okay, what is the reaction rate not constant? At the beginning of the reaction, when the concentration of reactant molecule is still high, it means there are many reactant molecules in the system. You can be see in the video with so many molecules, the chances of collisions between molecules are higher. Thus, more frequent collisions increase the chances of the reaction happening, so the reaction rate is faster. However, over time, the concentration of reactant molecules decrease because they are being used to form product. As the number of reactant molecules decreases, the chances of collisions between them also become less frequent. This results in the reaction rate slowing down as time goes on. So to make it clear, when there are more reactant molecules, they collide often, making the reaction faster. Over time, as reactant decrease, collisions happen less and the reaction slows down.
Okay, let's talk about the equilibrium dynamic or dynamic equilibrium. So the first one we can discuss about the type of chemical reaction based on their directionally, which is can be divided into two categories, one-way and two-way reaction. The first one is one-way or irreversible reaction. This is when the product form cannot be converted back to the reactant. This reaction represented by one-way arrow in the chemical equation. We can look at the slide. And the example is the reaction between sodium hydroxide and hydrochloric acid, which is produce sodium chloride and water. The one-way arrow indicates that sodium chloride and H2O cannot be transformed back into sodium dioxide and chloride acid. And then is the two-way or reversible reaction. In two-way or reversible reaction, the product can react again to form the original reactant. These reactions are represented by a double-headed arrow in the chemical equation. You can look at the slide. And the example is this reaction is between sulfur dioxide and oxygen to form sulfur trioxide. The double-headed arrow demonstrated that sulfur trioxide can decompose back into sulfur dioxide and oxygen. Okay, next, to comprehend the concept of dynamic equilibrium, let's consider an illustration using waters in two jars. In the slide, we have two jars. The one is closed jar and the one is open jar. But in equilibrium dynamic, we use the closed jar, or we can call it the closed system. So, when water in a closed system is heated, water molecules begin to evaporate, creating water vapor with a reaction rate we will call V1. The reaction can be written as H2O liquid become H2O gas. Because the system is closed, the water vapor can escape and will condense back into liquid with a reaction rate we will call V2, or H2O gas become H2O liquid. These two reactions, evaporation and condensation, occurs continuously and simultaneously. Initially, the evaporation rate, or V1, is higher than the condensation rate, or V2. After reaching a certain point, the rates become equal. This state is called dynamic equilibrium, represented by a double-headed arrow, H2O liquid and H2O gas. We can conclude that the dynamic equilibrium is state where reactions continue to occur and the rate of product formation equals the rate of reactant information. Okay, let's talk about the characteristic of dynamic equilibrium. The first one is that the reaction is bidirectional and occurs continuously. Number two, it takes place in a closed system with constant temperature and pressure. Number three is that the rate of the reaction toward the product equals to the rate of the reaction toward the reactant. Number four is that there are no observable macroscopic changes or visible changes, but in microscopic changes occur that change at the particle level that are not visible. So look at the graphic that on the slide. The change in reactant and product concentration from the beginning of the reaction to achieving dynamic equilibrium can be described that at the initial stage, reactants are at their maximum concentration and no product have formed. As the reaction progresses, the concentration of reactant decreases while the concentration of product increases. At a certain point, the concentration of products and reactant appears constant. The reactant no longer decreases and the product no longer increases. So this is the stage of dynamic equilibrium called. We move to the another slide. We have the factor that affecting the shift in equilibrium. So a system at equilibrium can change when influenced by external factors. These changes aim to achieve a new equilibrium and are referred to as a shift in equilibrium. So the first factor is that the concentration. If the concentration of a substance is increased, the equilibrium will shift away from the substance. And if the concentration of a substance is decreased, the equilibrium will shift toward that substance. The factor number two, we have the temperature. If delta H is positive, the reaction toward the product is endothermic and the reaction toward the reactant is exothermic. But if delta H is negative, the reaction toward the product is exothermic and the reaction toward the reactant is endothermic. According to the Cavalier principle, if the temperature is increased, the equilibrium will shift toward the endothermic reaction. And if the temperature is decreased, the equilibrium will shift toward the exothermic reaction. The factor number three is that the pressure and the volume. So increasing pressure or decreasing volume will prompt the system to minimize the effect of pressure by reducing the number of molecules. A decrease in the number of molecules leads to fewer collisions with the walls of the container, thus minimizing the increase in pressure. Increasing pressure or decreasing volume will shift the equilibrium toward the side with the fewest molecules. Here the mole ratio is equal to the coefficient ratio. When increasing pressure or decreasing volume will shift the equilibrium toward the side with the smallest total reaction coefficient. But when the increasing pressure or increasing volume will shift the equilibrium toward the side with a large total reaction coefficient.
Okay, in this section, we understand dynamic equilibrium in dynamic equilibrium. Dynamic refers to dynamic equilibrium, which is a concept in chemistry. Dynamic equilibrium occurs when the rate of the forward reaction is equal to the rate of reverse reaction. In this condition, the concentration of reactants and product does not change even though the reaction occurs simultaneously and continuously. We can see here there is an example of equilibrium reaction. Nitrogen tetroxide gas is in equilibrium with 2 moles of nitrogen dioxide. What is static equilibrium? Static equilibrium is defined as a state in which the macroscopic and microscopic properties of a system remain unchanged with time. It can be said that it is static equilibrium when 1. The vector sum of all external forces is 0. 2. The sum of moment of all external forces about any line is 0. And then 3. If the system velocity is also 0. So, in essence, an object is said to be in a state of static equilibrium if the object is not moving and all forces and moments of force acting on it cancel each other out. What is dynamic equilibrium? Dynamic equilibrium can be generally defined as the state of a system in which the macroscopic properties remain unchanged while the microscopic properties change. In mechanics, dynamic equilibrium can be specifically defined as the state of a system in which the system is in equilibrium, but its velocity is not zero. The system is moving at a constant velocity. In a chemical system, dynamic equilibrium occurs when the forward and reverse reaction occurs at the same rate in a reversible reaction. The concentration of reactants and product remain unchanged, but some reactants are converted to product and products are converted to reactants. However, these two opposing processes occur at the same rate. It can be seen in the image on the side that is state. Macroscopically, there is no visible change. The system is said to be in a state of dynamic equilibrium, which means that the reaction to the right and to the left continue, but at the same rate. Some difference between static and dynamic equilibrium. 1. In static equilibrium, the microscopic and macroscopic properties remain unchanged, where in dynamic equilibrium, the microscopic properties change while the microscopic properties remain unchanged. 2. In mechanics, a system without unbalanced external force and external moment can be considered to be in equilibrium. Also, if the system is stationary, it is in static equilibrium, and if it is moving at a constant velocity, it is in dynamic equilibrium. 3. In a thermodynamic system, if the temperature is constant and the input and output of heat and mass transfer are at the same rate, the system is in dynamic or thermodynamic equilibrium. 4. In a chemical system, if the rates of the forward and backward reaction are equal, the system is said to be in dynamic equilibrium. Okay, next, chemical equilibrium, although it appears static with constant concentration of substance, is actually a dynamic process at the molecular level. The forward and reverse reaction continue simultaneously, but their rates are the same so that there is no net change in the total concentration of the substance. Why does the concentration remain constant? Since the rates of the forward and reverse reaction are the same, the number of molecules formed is equal to the number of molecules decomposed, and this state is called dynamic equilibrium because even though there is activity at the molecular level, the overall system appears static.